Okay, very good. Today we have Ilija Buric from Pisa University talking about universal spinning Casimir equations and their solutions. We thank you, Ilija, for accepting our invitation, and please take it away.
Thanks a lot for having me. I'm very glad to speak here and have very good memories of Porta from earlier this year. I will be talking about this recent paper with Volker Schomerus about universal Casimir equations and the way to solve them. And I should also mention that some of very important ideas were discussed with Francesco Russo, who is a PhD student here in a related project. So, okay, this is not moving now. Now it is, okay. So in general, the topic that I will be talking about concerns two problems. One is partial wave decompositions in field theory, and the other is just quantum mechanics, so integrable many-body Schrödinger problems. These two types of problems are related because, in a sense, they are both related to the same question in harmonic analysis. And in this talk, harmonic analysis, I will always mean harmonic analysis on some Lie group. So more specifically, an example that one should have in mind is 4-point conformal blocks that can be related to wave functions of certain Calogero-Sutherland Hamiltonian that I will talk about later. And both of these classes of functions are related to what is called spherical functions on the conformal group. And these relations in the talk will make them spinning. So this is the main aim of the talk. And actually, I won't be talking about 4-point blocks so much, but this is certainly one of the examples of these relations. So just to say a few words quickly about the two problems in question. Partial waves, as I guess everyone is familiar, when we have some correlator or some amplitude in a field theory and want to separate its dynamical part from the kinematically fixed part, then this amplitude is expanded in partial waves. And partial waves, some contributions over intermediate states of some fixed representation of a certain symmetry group. So in ordinary quantum field theory, this would be spinning over all states of some spin. And this partial wave is this function PJD, which is a Gegenbauer polynomial of the scattering angle. And then the amplitude is some dynamical function of the energy times this partial wave is expanded in this way. And completely similarly in conformal field theory, we decompose a 4-point function into fixed functions and dynamical OP coefficients. And now the partial waves sum over a single conformal multiplet, and they depend on two variables. So one of the most popular ways and most used ones in the last 12 or 15 years is to solve for partial waves using differential equations that they satisfy. So this was first introduced, this method, by Dolan and Osborne, who derived the second-order equation called the Casimir equation for partial waves, and then solved it in terms of hypergeometric functions in 2 and 4 dimensions. In 3 dimensions, there is no closed form solution, but still having the differential equation is very useful, and one can, from there, learn various properties of waves or develop series expansions. For this was done for scalar fields, and now the most used method to to construct partial waves for spinning correlators, for correlators of spinning fields, is to act on these scalar blocks by certain covariant differential operators. So this was already, well, first class of these operators, I think, was first introduced in this paper by Miguel, João, David, and Slava, and later it was generalized to another type of operators called the weight shifting operators. And this method is very general, and certainly it will inspire some of the things that I will say in the talk. Okay, so apart from 4-point functions, which is the canonical example, there are also interesting correlators that admit similar expansions, and about these correlators, not so much is known to various degrees. So in defect conformal field theories or super conformal field theories, and then a lot less about higher point functions. Okay, so I won't say now more about this, but later. And the other problem on the integrable Schrödinger side is this Calogero-Sutherland problem. So this is a one-dimensional many-body system, so where you have n particles on a line, and these particles interact pairwise through, well, in this talk, it will be this sinh squared, inverse sinh squared potential. So this is the Sutherland version. The Calogero version is 1 over x squared. And the problem is integrable, and in a sense that this Hamiltonian fits into a family of commuting operators whose number is equal to the number of coordinates, and eigenfunctions of this Hamiltonian have been constructed. Now, this Hamiltonian that I wrote is not quite the one that will appear. So here the potential depends on differences of coordinates, but it was observed that also some similar looking Hamiltonians where there are also some sums of coordinates, for example, are also integrable. And the underlying reason for integrability of this more general class of systems was explained by Orslanetsky and Perelomov. They realized that this Hamiltonian arises by symmetry reduction of the Laplace operator on a Lie group. And from this observation, the integrability immediately follows, because the Laplacian is the quadratic Casimir, and the first integrals are higher Casimirs, and they're always the correct number of them. There's always the correct number. And these, from this group theoretic origin, these Hamiltonians are naturally associated to root systems. And these roots, Calogero-Sutherland models associated to root systems were solved by Heckman and Optam, and the wave functions are not expressible in general in terms of standard hypergeometric functions. They are called Heckman-Optam hypergeometric functions. So many properties of these functions are known and series expansions, but they are not like products of 2F1s, as we know for conformal blocks as well. So one more important thing for this talk will be that these models can be easily made spinning. So this model doesn't have any spin degrees of freedom at the moment, which I wrote, but they can be added in a natural way, as I will explain. So where does harmonic analysis come in? So, well, one relation I already mentioned, this observation by Orslanetsky and Perelomov, and the functions on the group which become wave functions of the Calogero-Sutherland Hamiltonian are called spherical functions. So this is a very important class of functions on the group, and they're kind of higher higher dimensional Legendre polynomials. And in the context of CFT, it was realized that the word identities for a 4-point function can be interpreted as these spherical conditions for some function on a Lie group. This was done by Volker, Misha Isachenkov, and Zhenya Sobko. And in this way, the spherical functions which solve the Laplace equation were connected to conformal blocks for the 4-point function. So these are the two steps, this observation and later then the observation by Oshanyetsky and Perelomov. And in the end, we get that conformal blocks are these wave functions, at least in the scalar case. So yes, I will start from the observation that there is a tool in harmonic analysis called Harish-Chandra's radial component map, which allows to write down the spinning versions of these equations. So essentially without any calculation. And then to find solutions, we will use some algebra of shifting operators using two constructions. So there will be, first of all, the Hamiltonians will be operators on one space, different Hamiltonians for different systems, will form a family labeled by some quantum numbers. And then we will have certain external weight shifting operators which raise these external quantum numbers, and then the internal shifting operators which change the eigenvalue. And the Heckman-Opdam hypergeometric functions would be something like ground states. And then by acting with weight shifting operators on these, one will get the eigenfunctions of spinning models and in turn spinning conformal blocks. So the applications that I will discuss are about 2-point function of symmetric traceless tensors in defect CFT, where the codimension of the defect is 2. And then 2 applications to higher point functions. Yeah, this is in kind of early stages, but yes, yeah, okay. So this is the plan. And one more comment before I start. So all the equations will be the special case of this operator here. So this is a differential operator in 2 variables, and these are cross ratios, T1 and T2. They're related to Z and Z bar in a simple way. And then this operator has, so the denominators, like there's the sums, the differences, and the 2 variables themselves. So these, in a sense, run over a root system, these variables on the bottom. And then on the top, there are some m's, m primes, d's, and d primes. So if I set all these things to 0, the operator is what is known as the Calogero-Sutherland model, the scalar one. And these you can see as kind of universal spinning variables where they satisfy the commutation relations of the rotation algebra, but they're not at this point matrices. So if I want, I can replace m's and m primes by matrices in any representations of the rotation group, and this becomes then a matrix valued Hamiltonian. So I will come to this, but basically the point that I want to make is if you start from this Hamiltonian and make some simple substitutions, these are all the equations that I will have are obtained in this way. Okay, so if there are any questions, of course, just ask. Otherwise, I continue. So let's start with an example of what is this radial component map. So the radial component map, allows to compute, to reduce differential operators when they act on these spherical functions. So let's take the one-dimensional conformal group. And the maximal compact subgroup is the U1. And in these conventions, it's generated by P minus K, and one can parameterize the group by Euler angles. And then it's an exercise that the Laplace-Beltrami operator on the group in Euler angles is this. But I want to ask a question: if I have a function that transforms in a definite way under the left and right covariance, under left and right translations by this maximal compact subgroup, how to act on the Laplacian on this class of functions. And okay, here it's I can just replace d by d phi by a constant im, and d by d psi by I minus in, and plug it in here, and I get some operator delta mn. And if I want to find eigenfunctions, these are hypergeometric functions. But the point is that you shouldn't need to compute the operator in 3 variables and then reduce it to 1, but that there is a way to directly go to delta mn without going to the full Laplacian. And okay, in this example, it's not very important, but for a conformal group, let's say in 4 dimensions, the group has 15 generators, and for a 4-point function, there are 2 cross ratios, so we want to reduce from 15 to 2. So the way you reduce it is the following. So Laplacian is the quadratic Casimir, and the quadratic Casimir, okay, it's d squared plus a half pk, anti-commutator. So the prescription is the following. I rewrite this in terms of a new basis, which consists of d, then y, which is this maximal compact generator, and y prime, which is the conjugate of the maximal compact generator by some fixed dilation. So here is h is a dilation, y is this, and y prime is the conjugate. So in this basis, I will rewrite the operator and get in this form, but I also impose the ordering that y prime always goes to the left and y always goes to the right. And if I impose these rules, this is the expression, which is easy to obtain. And then the statement is, this is Harish-Chandra's theorem applied to this example, would tell you that you replace on the right-hand side d by partial derivative with respect to the coordinate, and then y prime and y by numbers, and that this should give you the operator on this space, which in this example is clearly true. Okay, so this radial decomposition also can be used to construct raising and lowering operators for, well, they're raising and lowering operators on the group, but they will become these shift operators. So if I take the raising and lowering operators for y, they're these things, and I again apply the same prescription. So write them in terms of dy and y prime, and then make the same substitutions as before, these ones. I get these 2 operators, p plus and p minus, and you can check directly that they satisfy certain exchange relations with the Hamiltonians, with the Laplacian. So these relations tell me that p plus raises n by 1. So if I act on an eigenfunction of delta mn, with p plus, I get an eigenfunction of delta mn plus 1. And there is the lowering guy, and there is a pair of operators which raise and lower M, which are constructed analogously. So in that sense, if I compute the eigenfunctions of delta 0, 0, I can act on them with P plus minus and the other two to get all the eigenfunctions. Of course, this is an overkill in this example because delta Mn directly can be solved in terms of hypergeometric functions, but okay. You can also solve it in this way. Okay, so now let me briefly say what is the general setup where a manipulation like this can be done, and then I will say what is the conformal field theory setup where this can be applied. So we start from general, from a simple Lie group, and so this was the one-dimensional conformal group, and this subgroup K, it was the U1 before. The generalization, the proper generalization is that it should be a group fixed by a Cartan involution, so that the G by K is a symmetric space. It's fixed by a second order automorphism of the Lie algebra. And then the space of spherical functions is defined as the space of vector valued functions on the group. It's specified in terms of two representations of K, two finite dimensional representations. And so these are the functions which are covariant with respect to both left and right action of K, and the covariance properties are encoded by rho and sigma respectively. The examples are this, and okay, such a pair of groups is called the Gelfand pair, K. The most important class of examples for this talk will be when G is an orthogonal group, let's say SOMN, and then SOM times SON is a spherical subgroup. And here the signature is not important. So I can also take SOM plus 1, N minus 1, or something like that. All the manipulations will be completely algebraic. So yes. And what are these spherical functions? What are the examples of them? Well, the examples are found about among matrix elements. So if I take an irreducible pi of G and consider a collection of matrix elements pi alpha, A alpha, where A transforms in rho and alpha transforms in sigma. So pi needs to contain both rho and sigma when I restrict it to K. But if I do this, then this collection of matrix elements transforms in the correct way, and it is a spherical function. So essentially, in the group theory, we are just computing some matrix elements. Okay, so when we have such a setup, the starting point is the Cartan decomposition. So there are various versions, and we'll use at least two of them. So it's a decomposition of the Lie algebra into K, and then its orthogonal complement, which I call P. And then there is a kind of root space decomposition, but not the standard root space decomposition, but modified to include for this K. So I take the maximal abelian subspace of P, and then its centralizer in K is called M. And then the rest of the Lie algebra is decomposed into root spaces, but root spaces with respect only to A and not to the full Cartan. So this is called the restricted root space decomposition. And then some theory tells you that the universal enveloping algebra admits a factorization into A times into U universal enveloping algebra of A times U of K 2 times. So on the group level, the composition is KAK. Every group element can be factorized in this way. And this was the the composition, the factorization into Euler angles for SO2, 1. So the important thing here is that A is abelian. And so now, if you remember, spherical functions had fixed laws, how they transform under K. So obviously, if I know how a spherical function restricts to A, I can extend it to the whole group by covariance laws, because I have this decomposition. However, I cannot start from an arbitrary function, and somehow what measures this constraint on restrictions of spherical functions to A is this centralizer of A in K, this group M, and when you consider this, it means that, well, basically, because of the existence of this centralizer, the Cartan decomposition is highly non-unique, and then function, in order to be extendable, has to take values in M invariants in this vector space. So it's a vector valued function, but actually it takes values in a small subspace of this hom W right, W left. Okay. So now the Harish-Chandra theorem is about computing radial parts of differential operators. It tells you the following. If I take a differential operator on the group, regarded as an element of the universal enveloping algebra, and apply it to some function, to some spherical function f, I want to compute this to the restriction of this operation to AP. So, but yeah, I want to do it without going to the full group. And then the radial component map is saying that the theorem is saying that you need to apply this radial component map to U, and then with this you act directly on the restriction of F. So formally, this radial component map goes from universal enveloping algebra of G to differential operators in AP with coefficients in 2 copies of U of K. So basically, these are differential operators, and then these coefficients you can make into matrices by replacing abstract elements of the algebra with their representatives in rho and sigma. And the way you compute for any given element its radial decomposition is that you write it in terms of generators of this abelian subalgebra AP, and then kind of modified roots. So there are these restricted root vectors, which are analogs of ordinary root vectors, but for these Gelfand pairs, you decompose them into K part and P part, where K and P were these here, and you write any element, in terms of H's, Y's, and Y primes, and this is exactly what we did in the example. And after you write an element like this, you impose the ordering that Y primes should go to the left and Y's should go to the right. And okay, luckily, it's relatively complicated for an arbitrary element of the universal enveloping algebra to make this decomposition, especially if it's of very high order. But if it's, for example, of a linear element, it's very easy. Or if it's a Casimir, there is a formula, it's known how it's done. And this is the radial decomposition of the Casimir. So basically there is a part which is just the sum of hi squares, and then another part which depends on the roots of this the restricted root space decomposition. And this is how the relation to Calogero-Sutherland models comes about. Because if you conjugate out the first order terms, so yes, so now the prescription is that these h's are replaced by partial derivatives. And now if you conjugate out the first order term in order to get a Schrödinger operator, this is the Calogero-Sutherland Hamiltonian. Okay. So here alpha are these restricted roots. So I will give examples in one slide time. Just before that, I want to describe these shift operators. So there are two kind of natural constructions that one can do. One is to act on spherical functions by invariant vector fields, by first order operators in the universal enveloping algebra. And because these invariant vector fields, they don't commute with K, they will in general shift the covariance law. So if you act on a spherical function, you produce something which is no longer a spherical function. So you shouldn't act with them individually, but if you collect the generators according to how they transform under K, then these will modify the covariance laws in a definite way. So if I take a singly reducible representation in G under the adjoint action of K and group all these operators act on a spherical function, this will tensor the covariance law by the corresponding representation. So I'll get a spherical function in this new space. And with acting on right or left invariant vector fields, you can either shift the left or right covariance law. So this is the first. Now this, of course, this representation will be typically reducible when you do this sigma times pi, but I will explain how to project out without using any Clebsch-Gordan coefficients, which are in general hard to compute, how to project out the representations that you don't want. So these are the external weight shifting operators. They change rho and sigma. And the other type of operators that one would like to have is the internal ones that keep rho and sigma the same, but change pi. So if I want matrix elements of a different representation, but with the same covariance laws, this construction will make use of the fact that if I multiply a spherical function by a trivial spherical function with trivial covariance laws, then I get again a spherical function with my initial covariance laws. And from the perspective of matrix elements, this is like a tensor product decomposition written in terms of matrix elements. And there will be many terms on the right-hand side for, well, there will be infinitely many terms if I have a non-compact group. But if I have a compact group G, this decomposition is finite. And there are a few terms in general. But on the right-hand side, all the terms have the same A and alpha. So they have the same left and right covariance laws. The only difference is that they are of different representations. But this means that I can distinguish parts of this sum by the value of the Casimir. And this commutes with the radial component map. So yeah, the thing that I wanted to say before is that for both these constructions commute with taking radial components, and this is why in the end we'll get some reasonable expressions. So here I will do the dumbest thing possible, just project out all the representations that I don't want. If I want a particular representation, which I called here pi n, and I know that it appears in some tensor product, I will just project out the first n-1 representations and land on it. But this expression is not terrible if you apply the radial component map to both sides. Okay, so to give an example, if I take so the number of coordinates of the dimension of A, I forgot to say, is called the real rank of the pair, and it's essentially the size of the system, the number of variables on which the spherical functions depend. So this is an example of rank 1, where we'll take G to be the conformal group and the Euclidean conformal group, and K to be the maximal compact sub. We'll be interested for applications in conformal field theory in cases with rank 1 and 2. But if you go through the prescription, this is the radial decomposition of the Casimir operator of SOD plus 1,1. So I have AP, what I called AP, is generated by dilations. This centralized RAM consists of rotations. There are two root spaces, which are translations and special conformal transformations. And then Y's are, so I decompose a translation into sum of two parts, and translation is L1 mu plus L0 mu, and turns out that Y is L1 mu. And Y primes I can then conjugate by this dilation, and this is the expression. So and then plugging in the formula, this is the radial decomposition. So there are only two roots, but root spaces are highly degenerate. They're of dimension D. There are D translations and D special conformal transformations. And then what about weight shifting, external ones? So I see that G, when I decompose it in SOD plus 1, I have the adjoint, SOD plus 1 itself, and then I have the vector, which is the first row, L0I. So here indices mu run from 2 to D plus 1, and I don't know if I use on slides I, but they would run from 1 to D plus 1. So the first row transforms in a vector, and these L01 and L0 mu together form a vector, and these are the radial decompositions. And these expressions will come in shortly in applications. Yeah. So the second example, which is the one relevant for 4-point functions, for example, is when G is the conformal group and K is the subgroup of dilations and rotations. And then this is the decomposition of the Casimir, but it's a little simplified. So first of all, I conjugated out the first order term. This is a minor point, but I also put all the primed stuff to 0, just to make it fit into a slide. But this is kind of a simplified radial decomposition. And in this case, there are two, it's a rank 2 system, which, well, by the way, so the rank for this general pair SOM times SON is the smaller of the numbers M and N. So this is the way how to read the rank. So in this case, it's SO1, 1 that determines the rank, which is 2. So this is the Casimir, and then there are two weight shifting operators, because P and K, they transform both as vectors under rotations, and they have dilation weights plus minus 1. So, and these are the radial decompositions of translations, and this A should be small a on the left. Okay, so just to make some comments. Okay, so the name of shifting operators comes after the quantum numbers being shifted. So if I shift rho and sigma, this is like shifting external quantum numbers in field theory. And if I shift pi, this is like exchanged field. Yes, so this is the second comment is what I said, that these constructions commute with taking radial components, that rho times pi is not irreducible, but we'll need an extra projection. Yes, so an important point is that in using internal weight shifting, this we'll actually start from an analog compact problem. So we'll start from a problem where we compute some matrix elements of a group SOD plus 2, the compact group, and then in this case, the internal weight shifting procedure is finite. There is only a finite number of projections that needs to be done. But then after this is solved in the compact case, one can analytically continue solutions to non-compact cases and check that they satisfy all the right properties. Okay, so the number, if you want to compute some spherical function using these shifting operators, the number of applications of operators scales with these external quantum numbers. So this is roughly, if you have very high representations, rho and sigma, you will need lots of steps, but if they're reasonable, then in not many steps, you will construct this. And as I said, will not require any Clebsch coordinate coefficients or projectors. Okay, so yeah, one more technical point. We will always use function space realizations for finite dimensional representations. And this comes from the following facts that I said that these functions, restrictions of spherical functions are highly constrained, but these constraints are nicely expressed in these function space realizations. So if I have a symmetric traceless tensor, I can write this representation as differential operators acting on polynomials. So this is a finite dimensional representation because these polynomials are required to have some bounded degree. And this expression is similar to conformal, to the representation of the conformal algebra on a primary field, just delta becomes a minus L. So this first quantum number is minus the spin. So, and then, for example, if I have two symmetric traceless tensors, rho and sigma, the question, what are the SOD invariants? So this is for this case where G is equal to the conformal group and K is the maximum compact subgroup, then the stabilizer M is SOD. And there is a unique invariant combination of these coordinates. So functions of this coordinate Y defined as the argument of F in this equation are precisely M invariants. So, and because the original functions are polynomials, the M invariant functions are just polynomials in Y of some bounded degree. So, and this, the choice of this function space realization is usually clear from the problem. Like this is chosen so that these conditions are expressed relatively easily, the same invariance condition. Okay, so if there are some questions, I will answer them, and otherwise I will go to applications to CFTs. The general class of systems that fall under this spherical function category are 2-point functions of defects. By defect, I mean a subspace of the Euclidean space. And the property that is important is that the stabilizer of a defect is a spherical function. So inside the conformal group, the rotations around the defect and conformal transformations along the defect are those conformal transformations that preserve this space, and this is always a spherical subgroup. So I will use this slightly formal point that a pair of points may be regarded as a zero-dimensional defect, and I mean a pair of points is stabilized by dilations and translations. Sorry, dilations and rotations. And then there is whenever you have something like this, the argument why this is a spherical function is as follows. If I take a 2-point function of this defect, the configuration space is twice G over the little group, and then imposing the word identities means taking the G invariants in this space of functions. So I cancel one of the G's inside with the G outside, and I get G twice divided by K. So this is the space of KK invariant functions that we considered before. And this is, of course, very sketchy, but and this is for scalars, but if the objects are spinning, there are precise maps which take the space of solutions toward identities to spherical functions, so bijections between these two spaces. These we developed over the last few years for the 4-point functions and some 2-point functions in presence of defects, and I will just consider them as known and not really discuss them in any detail. So one more point is that if the defects don't have the same dimension, in general, this discussion doesn't go through. But if their dimensions are related in this way, the groups, the stability groups have the same Lie algebra, the same complexified Lie algebra. So still, these cases fall under this category. And for this reason, the 2-point function of local fields in the presence of a codimension 2 defect is also modeled by a spherical function. So the other class of examples will be the defect channel in a defect CFT. And this comes from a fact that a single bulk point, the stabilizer of a single bulk point inside a defect conformal group is again spherical. And this is like a rank 2 system, but it's a product of 2 rank 1 systems, because both the defect conformal group and the stabilizer are of this product form. And then I will discuss some applications to higher point functions at the end. Okay, so this is the setup. And this setup was also studied quite extensively in this paper by Edo, Marco, and Emilio. So we'll have 2 symmetric traceless tensors of spin Ji in any dimension and in the presence of a codimension 2 defect. And so this system is interesting. There is a crossing equation where you can expand the 2-point function either in the bulk channel where you fuse the 2 fields in the bulk, and this is like just in the ordinary CFT, and then the resulting field is expanded in defect excitations, or the defect channel where each of the fields is expanded in defect fields, and then one takes the 2-point function of the defect fields. And we'll treat the 2 channels in turn, and I think I have 4 slides per channel, but really with the radial component map, there is very little to do. So let's start with the defect channel. First, what are the quantum numbers that characterize the blocks here? Well, they're the quantum numbers of the exchanged field on the defect. So the 2 fields have to be the same in order to have the same quantum numbers in order to have a non-vanishing two-point function. So we have a single set of quantum numbers for the defect field, which are delta hat, L hat, and S. S is the transverse spin, and L hat is the parallel spin. And then there are two tensor structure labels, because when the bulk field is spinning, the two-point function of a bulk and the defect field is not uniquely fixed. There is a finite number of tensor structures. So in total, we have 5 quantum numbers, and the dependence of this S is just an exponential. So I will not talk about S. I will just talk about this function with 4 labels. So this correlator is mapped to a spherical function where G is the defect conformal group, and I'm taking only the parallel part. K is the maximal compact subgroup, so this is rank 1 system, and then rho and sigma are determined in terms of bulk spins. So there are restrictions of bulk spins from SOD to SOD minus 1. So both rho and sigma will be reducible representations, 0 plus 1 plus ... plus J. And these L and L prime labels fix a single irreducible component of rho and sigma. So I will fix this to begin with. So now we have the 2 more labels. So when you write down the radial component map, you get this operator. So there are 2 variables here. This variable lambda is the cross ratio, and then this variable y is this variable that I showed before, the spin cross ratio. So it's defined here. So this is the Hamiltonian. Sorry, not the Hamiltonian, the Laplacian, because I kept the first order term, and where this D is the Gegenbauer polynomial. So this is the expression. And now this essentially solves it by itself. I mean, first of all, you can see that this operator stabilizes on polynomial functions in Y, and the degree of these polynomials is the smaller of the numbers L and L prime. Okay, and this is the asymptotic condition, the boundary condition that blocks satisfy, which is lambda equals to infinity is the bulk to defect limit from where you can read this asymptotic behavior. So now weight shifting operators are these 2. So if you remember the expression for invariant vector fields, there is a cot times something minus 1 over sinh times something. So these are the operators, first order operators. And they satisfy these exchange relations. So the Q lifts L by 1 and Q bar lifts L prime by 1. Finally, we need the scalar solutions. These are the scalar blocks. These are hypergeometric functions. And with this, we generate arbitrary conformal blocks. So if I want to compute this function, so here there is an additional index P, which is the dimension of the defect. Okay, I think I didn't write it in some of the formulas explicitly that this depends on P. But okay, we wish to compute this function psi. So, and there the algorithm then is as follows. I start from a zonal spherical function, and I raise the zonal spherical function would have P delta hat 0 and then 0, 0 in the upper indices. And then I can raise this to L hat by external shifting. Once I do that, I multiply this result by another zonal, but with you see the second lower argument here is minus delta hat, and this will ensure that among the irreducible components that I will generate, there will be this delta hat L hat guy is one of the components. And so the projection is done how I briefly described before, and I will show in the example. So, and once you have this function, you can raise the appropriate number of times this L hat to the first one to L and the second one to L prime. And this gives the function that we wish to compute. I mean, the reason that one needs to kind of do the first and then the second and then the first again is that this exchange of delta and L hat can only happen if the external fields are have at least L hat spin. So I need to first go to this function, which is the smallest set of external quantum numbers, which has the right exchanged quantum numbers. So okay, this is an example, so I started with psi1 delta 0. I want to compute for exchange of L hat equals to 1. So in the second step, the projection is this. So j times 1 has three terms. I want to project to j comma 1. So I need to subtract the other two terms, and these are these two projections. And the operators on the right hand side, this p is the operator that I gave here. And this first function is the computed by external weight shifting. Okay, so quickly about the bulk chain. How much time do I have? 5 minutes? Do I have 5?
I think you have 5 to 10 minutes.
Okay, thanks. So it's almost the same. Let me just discuss the quantum numbers which characterize these blocks and why there are 5 of them. So here we fuse the two fields in the bulk. So because these are symmetric traceless tensors, you would expect a mixed symmetry tensor to be exchanged. But because the defect has codimension 2, it can only couple to a symmetric traceless tensor. So in fact, you only have 2 quantum numbers of a symmetric traceless tensor for the exchanged field. These are this delta and j. And then little j, iota, and m are additional 3 numbers for tensor structures. And indeed, the 3-point function of symmetric traceless tensors in the bulk has 3 quantum numbers. So, okay, so this correlator is mapped to a rank 2 spherical function with the conformal group, and k is then rotations and dilations, and it's a one-sided system when the left representation is trivial and the right representation is the product of the 2 bulk field representations. So it's j1 times j2. Again, so as we had before, sigma is reducible. So the first step is to fix a single irreducible component, and this fixes 2 of the quantum numbers, these little j and iota. And we had 3 more. And in fact, this m will now be a label of different eigenfunctions of the same Hamiltonian. Before we had for every Hamiltonian a single eigenfunction. Now there will be multiple eigenfunctions of the same Hamiltonian. Okay, so again, this is the Casimir operator, which you write down. It has two variables and then the kind of compact variable x, and it stabilizes this operator on polynomials of x of degree j minus iota or less. and conformal block satisfies some boundary conditions. The case where J is equal to iota, then this stabilizes just on polynomials of degree 0. And the eigenfunctions are just in T1 and T2, and these are the scalar conformal blocks. And these functions are very well known. So we want to move from these systems to systems which have the iota smaller than J. So this first index here was the J index, and the second lower index is the iota index. And B is related to conformal dimensions of the external fields as delta 3 minus delta 4. Sorry, 2B is delta 3 minus delta 4. And okay, so the operator P, the weight shifting operator is this operator Q. So again, if you compare to what we had in in these expressions, this cot T1 plus T2, okay, this should be, there is a cot missing here. It's not a half cot T1 minus T2, and then in these inches. So, okay, these are the weight shifting operators, and there is a similar, sorry, I'm giving a seminar here. I'm giving a seminar for another a few minutes, if you can.
You have a meeting?
Yes.
Oh, sorry.
Sorry for the interruption. So, and we have a similar operator P, which is, so Q is the lowering one and P is the raising one. And these are the exchange relations. So they both now, okay, so both Q and P raise J by 1, but we need two operators because every time you increase J, there are more solutions because polynomials, they're J minus iota solutions, actually. So what is the, so you have two weight shifting operators, and these actually would generate 2 to the J minus iota solutions if they were independent, but there is another relation between P and Q, so it means that actually you get precisely J minus Q solutions. And just to show how it works, if I want eigenfunctions which have J iota plus 2, I can start with the eigenfunctions that have J equals to iota and then apply either Q twice or P twice, or I can apply once P and once Q, but it doesn't matter because of the second relation, these two, the order of P and Q doesn't matter, so I get 3 solutions, which is, yeah, J minus iota plus 1 is the number of solutions that you should have. Okay, so this is the, and yeah, this generates all conformal blocks. In this case, we don't need internal weight shifting. If you had mixed symmetry tensors, then one would also need some internal weight shifting, but it would work in the same way as before. So now, yeah, just briefly to mention these other more exotic applications. One is that okay, because these formulas work for any spin, they're useful in systems where arbitrarily large spin can be present. So in this example from last year, we looked at a 6-point function in some OP limit, where instead of 9 cross ratios, you only have 6. And this there is an integrable model called the Godin system, which produces 9 Hamiltonians for the original system, and in this limit, 6 of them remain independent. And in the limit, actually, you get 2 systems of 3 and 3 variables, and you can imagine like cutting this diagram in half. And the 6-point conformal blocks in this limit should factorize into products of 4-point conformal blocks for the left part of the diagram and the right part of the diagram. But these are spinning blocks, and the like the external spin, if you cut the diagram, the external spin on the right, for example, for the left part of the diagram, the external spin is a mixed symmetric tensor. And what we showed in that work was that if you take a limit from the 6-point system, and this is just 1/2, the limit of the Godin Hamiltonian becomes precisely the Calogero-Sutherland model, which you get from the radial component, where this mixed symmetry tensor is the external spin. And this is actually the same Hamiltonian that I showed before, because this defect system has the same Hamiltonian as this 4-point system. And the last application is this. Well, for a 3-point function, if you consider the system that we did before of 2 bulk fields and add a 1 field in the defect, so in the defect channel, this system, the blocks we computed before, and so we look at the bulk channel. And the idea is that you can treat this as a spherical function where one of the representations is infinite dimensional. But so it's not clear how to exactly solve it, but at least the differential equation is relatively simple. It's the same as before, just the variable x is now an honest variable, so the dependence on the third variable is not polynomial necessarily, but it can be any function. And we checked that this equation obtained by the radial component map can be mapped to an equation which you can derive in a standard way. Okay, so well, yeah, let me go to conclusions. Yes, so we got these. Well, these universal equations have been known since the 50s, but I guess the observation is that they apply to various systems in conformal field theory. And then from the universal formulas combined with this function space realizations, one gets families of Hamiltonians for different systems all on the same space. And the weight shifting operators act also on the same space. So they are no longer intertwiners between different systems, but they are actually differential operators which close into some set of exchange relations. Yes, and okay, these things I mentioned, there is a systematic way now to construct all these blocks, and yeah. So the questions that we would like to address in the future, there are many, but let's start with this defect setup. So the 3-point function, when you add the third point in the bulk, it also has a crossing equation like the 2-point function. So it would be interesting to study this. And actually, if we want to study it in the light cone limit, one can already do it, because in the light cone limit, the bulk channel simplifies drastically and you can compute the blocks. So there is no obstacle starting to look into this light cone bootstrap for this setup. Now, away from the limit, we know that there is a type of Godin model which produces a third commuting operator. So maybe also from that perspective, one can study this system more generally. Okay, about extensions, it's the supersymmetric version of this is quite interesting, because it's known that 4-point functions in superconformal field theories are also spherical on supergroups, and the reduced operators form an interesting algebra, which includes all the Casimirs, but there are some kind of Dirac operators as well. And yes, to understand this systematically and construct the blocks would be nice, I think. The generalization to asymmetric cosets would be important. There is I just don't know whether it's true or not. The radial component map works for cosets where you take K1 and K2 instead of twice K, but this would cover interesting physical systems. And finally, I think that, okay, so that these interrelations with Godin models are very interesting. And we understand that in some cases, Godin models become spinning Calogero-Sutherland, that we can make spinning Calogero-Sutherland models for higher point functions, which are also described by Godin models. So to understand these relations and maybe then to lift the solution generating techniques, which we now have for the Calogero-Sutherland models to the Godin case, this would be important. If it can be done, it would be very important. And lastly, for ordinary quantum field theory, also these methods apply for the scattering of photons and gravitons, and this is something that we are working on here in Pisa with Francesco and Alessandro Vicchi. Thanks.
Okay, guys, let's thank Ilija. No, yes, no. Okay, I think we have time for questions. So, any questions here?
Yeah, can you say something about monodromies? Like, are the monodromies known in these Godin models for some higher point?
I don't know for Godin. They are known for the scalar Calogero-Sutherland. Yeah, for Godin, I am not sure.
What about this Heckman-Opdam hypergeometric function that you said?
Yeah, for them, they're known, and I think they're known for Heckman-Opdam hypergeometric functions for any root system. So much more generally than what we used here, because here we only had a BC2 root system. Like for any BCN or AN, I think that monodromy is known.
Okay. But for instance, SOD, 2, what can you say about say SOD, 2 conformal blocks?
SOD, 2.
Yeah.
You mean
Lorentzian Euclid, Lorentzian conformal.
Yeah, well, okay. So, for example, here, I looked at conformal block. So this Hamiltonian is exact same Hamiltonian as you would write for a 4-point function of a mixed symmetric tensor, but the blocks here are not the 4-point conformal blocks. They have different boundary conditions. So in practice, how we do it is that we determine the boundary conditions for the scalar case, which is usually not so difficult, and then we check that the boundary conditions are preserved by all weight shifting operators, which they are. So these blocks, for example, are not scalar conformal blocks, even though the equation is the exact same equation as are not 4-point conformal blocks, even though the equation is exact same.
Okay.
Does this answer the question? Or?
Yeah, thanks.
Okay, I have another question. This formalism is very nice because you can find these weight shifting operators, and in particular, you can find for any representation, right? You never commented about mixed symmetry. You never showed any application of mixed symmetry, but you also had those, right?
Yeah, this is mixed symmetry. So
Yeah, but this is not the weight shifting, right?
Oh,
Okay.
yeah, yes. Sorry, the weight shifting operators extend to mixed symmetry. This is true for the internal ones. It's not obvious, but it turns out to be the case that, well, I checked up to mixed symmetry with 2 Young tableaus that you can always compute these external shifting operators. And then the internal ones are sort of, yeah, they follow from a very generic principle, so they're there always. But yeah, indeed, the external ones also survive I didn't compute them for higher than 2 row Young tableaus, but I expect that it will just continue to be to hold for.
Okay. How would you say, like in a line, how would you compare this formalism to the previous weight shifting one? Like in the previous one, you would have some, you also have coefficients. I think here you don't have any other coefficients to compute, but in the other one you have some weight shifting, you act on 2-point functions. There is some these relations between 2-point functions of different weights, but you shift one and shift the other such that the overall weight is the same, which I think is more or less the same as you did as projecting. You have the trivial action and then you project to the one you want. I think it's more or less the same story. But acting with weight shifting is to find, if you want to find a conformal block with a considerable spin, yeah, I think it's pretty slow to compute these things. How do you think this compares to that case? Like, it seems like you built a lot of solutions and then you have to project to the solution you want. I think it will also take a lot of time.
Yeah, that's right. I don't know if this can be optimized. So we didn't do large scale checks. So for example, I have more experience from this compact case, which is this that appears in the S matrix story, where the group is compact, and there somehow all conformal, all partial waves are polynomials, and in this case it works quite well actually. So the projections work quite fast whenever, for whatever quantum numbers that we wanted. It produces the block quickly. When in the non-compact case, it runs relatively slow. Indeed, like what you said, like if I put 2 stress tensors, I would need, like, I don't know, probably to do 5 projections or something like that. And it works relatively slow. Now, I don't know, maybe it can be optimized in some way. Again, I think if I expand the initial function in Taylor series, then it should work fast because I'm just applying a differential operator. But if I act on a hypergeometric function with the differential operator and then try to simplify, then it works relatively slow.
Okay, thanks. Any other question? Okay, so one last question. You can use this formalism to do something similar to what David and Valentina did, right? Like starting from a scalar, a higher point function, use these weight shifting operators and arrive to a spinning higher point function, right?
Well,
or is it preventing you from doing that computation and basically get the same result? But
it's not yet clear. So this is what I was saying at the end, that we would need to uplift these shift operators to the Godin model, and I think it. Well, yeah, it just one has to check if it can be done. But yeah, this is something that I've been discussing with with people. And
okay. Nice. Okay, thank you. I think there are no questions. And okay, Thank you,
Okay,
Ilija.
thanks.
We'll stop here. See ya.
Bye bye. Thank you.